this topic, which is simulation driven product development or product design. Very generic though, but it's very important. And industries over the time have realized the importance of simulation and are really working hard towards implementing it in a in a structured way and in a validated way. So with that, let me just give you an overview of today's webinar. As it is, product development, which is obviously simulation driven. So we will have, a few slides. We'll have a brief overview on how mechanical product development process works, how the process flow is, and what companies are trying to do. Are there any specific tools or some methodologies or process which organizations are leveraging to have a structured product development process or not? So we will talk little over that. Then we will also talk about how simulation, I mean, we'll walk basically mechanical simulation over different phases of product development. So how simulation is helpful in different phases of your mechanical product development. We'll talk little in more detail there. And as I said, simulation is definitely a big boon. Simulation has helped. How it has helped, some statistics from a few of the references. And then I also thought that in addition to this, let me also include some very frequent failure mode, which is fatigue, coming out of vibration or other pulsating loading. So I'll talk little about fatigue and what we do, what tools are used, or typically which algorithms are used to estimate the fatigue life. Okay, and that's how we'll walk over through this webinar. So to start with, I'll just let's assume one product in mind, so that we can map everything what we discuss with that product. So what I thought is, you might have seen the fuel tank in the trucks, okay, which is typically mounted, which you can see from outside, which is mounted somewhere at below the chassis. Okay, so we'll take example of that fuel tank, and maybe there is a fuel tank. You may need one pump inside fuel tank also to pump the fuel to the to the rail, or wherever you want to take it, the fuel to engine finally. Okay, so we'll take example of this fuel tank and maybe the pump inside the fuel tank. So whenever I take example, I'll try to take example from these two. I mean, this basically overall product. So how a typical product development process works. I mean, this is just a very macro level overview. So we typically there can be two type of typically, I mean, broadly there can be two type of processes. One is new product development, which is also known as NPD or NPI. And then there can be other, which is sustaining engineering or requisitions or something. So let's say sometimes in sustaining engineering or even in requisitions, you may not need to develop the entire product, but if you are working on very small, I mean of that system, a very small product, let's say one spring, you may still need to develop that spring. So this process of NPD can still be applied to the the development of new spring, okay, for your product. So what we do now, when we walk towards the product development, the very first thing comes is concept. Okay, we may have a team which is made of product engineers. Now people have different concepts. Let's say may not be spring, but let's say for bracket. Okay, we talk about fuel tank. Now fuel tank is mounted below the chassis, so you may need brackets to mount. Okay, now for those brackets, you may have different designs. Like typically some brackets may be heavy, may have more mass to take care of all deflections, everything. Few people may be smart to have some typically I type of sections or some ribs to provide stiffness to that. So all these concepts. So typically you work on the concepts. I mean you bring together all the concepts, then you choose few concepts, some 2-3 concepts. I'll talk over how typically people choose the concepts out of 10 concepts, let's say. We'll talk a little more about that later. Okay, so you pick now concept, Now you start, working towards design. Okay, you work on primary design, you work on, a very just outline of bracket. You try to decide your dimensions, decide your angle, decide your rib width and size. But this is at primary level, not really very detailed. Okay, and then you take that and get your prototype. Prototype again, there are 3D printing and rapid manufacturing available today, but few products or few components cannot be really 3D printed. I mean, if it is for functional check, you can still do 3D printing, but for few loading conditions, 3D printing may not be really good. So what you do is you typically, order your suppliers, let's say 100 or 1,000 such parts for prototyping. Then you get your prototype done. Then you test your prototype. You see if everything what we thought is working as we expected. Okay, and then you go for detailed design. This manufacturing, there is a difference between there are some phases between prototype and manufacture as well, because then it comes the detailed design. You work on optimization, you work on, you know uh, PPAP, which is production part approval process, about your manufacturer. Then you go to manufacturing, and finally it goes to delivery. Okay, so we'll talk on these little more in the coming slides. So okay, here, I mean, little one more level of detail here. So as you see on right hand side, what you have to understand markets or customers needs. So let's say, we took the example of our fuel tank and the pump inside that. Okay, customer says that, okay, I want this fuel tank of capacity, let's say, 500 liters. Okay, so now, okay, you get one requirement about the fuel tank size, and then customer wants, because it is for truck, and truck may have to travel on plain road, on terrains, or bumpy roads. So they may have their own requirements of, vibrations, because if you travel on bumpy roads, you'll get a lot of vibrations. Okay, so those vibration requirements come. Then truck may have to travel, in winter, in heavy summer, like maybe, if it is not for India only, if it is for US, or if it is for, Canada, if it is for Middle East, the temperatures can be too extremes. Okay, and then and 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 then you get, like, what if trucks meets with an accident. Okay, so kind of impact loadings, which are typically taken in form of G loads. So all these requirements. So what customers or what market tells you basically that, okay, I want the tank of this capacity. I don't want tank to fail in this particular, when there is a vibration. I don't want tank to fail when, truck meets an accident, and so on. Now let's say you have inside pump. So I don't want, the noise coming out of pump. I don't want, pump to get disintegrated or get failed. Okay, when the truck meets with some accident, or any bumps. So all these requirements come. Now you work on, okay, for pumps. Okay, if I want, the noise not to be more, I have to look for all these features. If I want the tank to sustain, all the temperature zones, all the, vibration levels, all the G loads, I need to have, okay, these features, this certain thickness of my, I mean, typically tanks are made of typically the tanks are made of plastic. Okay, so I have to have, this thickness at this location, and then I have to have this rib here, this stiffness member here, this type of bracket, the way it is, the tank is mounted to chassis. Okay, and then okay, this product design specifications, basically, again, these come from, you may have customer requirements. At the same time, you may have some requirements, coming from some standards. Okay, typically for aerospace automotive, you have some standards which have clear documentation of all the requirements, I mean, minimum requirements. On top of that, customers also can give you requirements from their side. Okay, and then okay, now this prototype here is, okay, now you decide on something. You have to build the prototype. The prototype building is needed. Now you may say that, okay, there is a simulation, but why we need to build a prototype? Not, I mean, I would say that, companies believe in simulation. Yes, they leverage simulation, but testing is a really an important part of any mechanical component. I mean, testing has to be done, because you may not be able to really identify the environmental variables, the few of the loads which are difficult to realize. Okay, and at the same time, the material condition, I mean, you may assume in simulation some very ideal material properties, or something which may be different from your what you get from your supplier. So yes, we need to have a testing done for sure. But testing now, testing may not be, I mean, testing samples, or the instances of testing may not be as many as previous when we did not have simulation. Okay, so you, okay, when you send it for prototype, you get to know about, let's say if it is plastic, you get to know about injection molding, all the limitations, what kind of thickness, minimum thickness you can give, because injection molding has its own limitation. Okay, warpage and a lot of other things. If you have sheet metal, then you have different limitations. So basically all these limitations you get to know. Okay, and then you kind of incorporate all those limitations. Okay, you work on fine tuning, you optimize your design, you kind of remove additional material, or you provide optimum stiffness. Okay, and that's how you get to detail design. Again, you design for manufacturing, design for excellence, design for assembly, you might have heard. Okay, so all these uh, uh, kind of process are used to get your final product. Okay, and then you there'll be again there'll be final testing before you really ship it to customer. Okay, customer, or you launch it in the market. So you do that, you certify your manufacturer, what I just mentioned about PPAP, production part approval process. Through that, you kind of certify that, okay, my manufacturer, let's say you have a company, B is your manufacturer. Now B might be your kind of in your list is your customer for, I mean, is your manufacturer for long time, but still new design will have certain changes, and those changes may not be really might have not got validated from that manufacturer. So the moment you have design changes, or you moment you have different type of processes, you go and you kind of have a process which is PPAP to basically certify the production which is coming out of your manufacturer, whether that meets your requirement or not. Okay, so okay, so now maybe this funnel, it shows you a kind of brief overview. So on the left hand side you see funnel, so product development, concept gathering. You have multiple things, literally multiple concepts by many people, they have their own ideas, own rationales. Okay, then you do basically preliminary design, and you test the prototype. Okay, and finally you come to little less concepts. Okay, you rather, and then you fine tune, you kind of because of limitations you may have a few concepts which are not working well. So you finally in the third stage you come with a little less number of concepts. Then you have prototype development and testing. So okay, so finally what you get is a kind of a filtered out, let's say out of 10 concepts, what you see is finally, let's say 2 and 3 concepts only will work, and really will go forward for the design. Okay, so now this process, and I mean this process, only if it is structured it can be followed well. So companies were facing some problem. They knew that, okay, this has to be done, but there was no structure, there was no kind of process. So in 1980 or so, Motorola came up with the Six Sigma, and then G brought DFSS, and followed it, and then many organizations came, and they kind of followed this approach because they observed excellent results out of this. So this Six Sigma approach, I mean, typically for product development, what we use is design for Six Sigma, which is DFSS. So this is a kind of structured approach to take forward the product design. Okay, and as you see here, it has typically these 4 major stages: define, characterize, optimize, verify. So we will not go into much detail here, but we'll still talk about a few important tools and what we use out of it. Now few companies on top of DFSS, they may have their customized product design process, which has leverage some tools of DFSS, some of their own tools. Okay, few companies may follow DFSS as it is proposed. Okay, so there are multiple versions. I mean, I have seen most of the companies, they have their own product development process or PDP, or typically whatever those organizations call it. But yeah, definitely these DFSS tools are well leveraged in all the even customized processes as well. Now, as you see at the bottom, you have get reviews. So these get reviews are nothing but, let's say if you have preliminary design, okay, you have concepts, you design something, you have preliminary design, you have prototype tested, and then it will be reviewed by your senior engineer or chief engineer, or some engineering leader, who has authority to approve that, okay, this will work, it meets your requirements, it meets all the standards, everything is okay, so now we can go ahead. And then you fine tune it, the design is fine tuned, and again you have gate review, then everything is signed off, okay, before production, again you have gate review. So all these milestones are basically just to verify that, okay, stage wise whatever is being done is done well. Okay, so so typically define, characterize, verify, optimize. Now this the first stage at the top is something which is defined. So we will talk a little more on that, and which is voice of customer, quality function deployment. This is more of gathering the requirements from customer, and this is more of failure mode, effect analysis, concept selection, pew metrics, everything comes here. Characterize. Then you have design of experiments, where you have multiple designs, you try to pick few designs which are you know giving you the desired results in optimized way, and then you try to get the reliability of the design, that try to check the robustness. Okay, now let's say I'll go little into a little deeper into what is voice of customer, what is QFD. So now, as I said, for pump and for tank, you voice of customer is, customer does not know your technical requirements. So what a customer gives you as, okay, I want the tank of this size, which can contain this much liter of fuel. Okay, maximum this much or minimum this much. Okay, it gives you okay certain that it should not fail in this condition, it should not fail in this temperature. Okay, it should be light, it should be less cost comes definitely. Quality and cost is something which is always there from customer. Okay, and then for pump, maybe noise, maybe uh, uh, a kind of a desired pressure to your rails. Okay, a desired pressure drop, and so on. So that is something which is in voice of customer. You're typically, your application engineers, or your those people who interact with customers, they try to gather all these requirements from customer. Okay, as told by customer. Okay, exactly as told by customer. Then what they try to do is they use this quality function deployment, or house of quality, what we know. So this is more of converting those requirements, which is what here. uh, okay, this what here. Now what is something which is coming from customers. So okay, this example here is very simple example, which is example of pizza. So what they say, it should be of good taste, low price, texture, maybe no fat or low fat, and then fresh and hot delivery, and so on. This is for pizza. Okay, for our technical, as I told you, for product, it may be, low price is always a customer requirement. Okay, then it can be like, a good quality, able to sustain all the temperature ranges, able to sustain uh, all type of, typically terrain, or road conditions. Then pump, should be less noise. So what you try to do is, here you try to get that, okay, now less quality, what should I get? I mean, how I get, sorry, less cost, how I should get the less cost. Here what you will have is, okay, now the material should be cheaper. Okay, my production process, my engineering cost, everything should be low. So what you try to do is, here you have all the watts which are given by customer, and here on this you have all the hows, as in how you are going to achieve that. Now quality, house of quality or quality function deployment, it may be at multiple level. You have at very top level, then you get at system level, then you get at subsystem level, then you get at. So let's say if you have tank and pump itself, let's say first you have a tank. Okay, now you get it, tank can be one component level, you can say. Okay, for this, the system level will be truck, then chassis, then tank, then inside tank maybe bracket, in maybe even below components maybe your bolts. Okay, for pump it may be pump assembly, then it may be inside your rotor if it's a rotary pump, then your different axes, then magnet, then electrical, and lot of things. So what you are trying to do here is you have kind of big wise, okay, and you are trying to get your small wise here. Okay, so you have customer requirements, you're trying to uh, basically derive your requirements for which you will be working. Okay, so now what you have here is you have score for everything. Okay, so basically let's say a low price may be related to material. Okay, but will low price really will your color, I mean, maybe color may not have strong relationship with pricing. Okay, whether you have green, red, or yellow, it may not really vary your price much. So okay, so the relationship here will be low relationship or loose relationship, but the strong relationship will come when you have on this axis, let's say material, and on this axis you have low price, then they are strongly correlated. Okay, so if you change the way, moment you change the material, the moment you reduce the material, your cost is going to get affected. Okay, so that's how you in this matrix you basically see how your what is related with your how, and then you rate them based on low, medium, and high. Okay, and how important is your what, I mean how important, let's say cost may be at cost may be of topmost importance, so cost score will be high here. I mean here may not be for pizza, but let's say for our product, so let's say the cost score is 10, and how it is related with material, let's say that is high relationship or strong relationship, which is you know 5. So 10 into 5, your score here will be 50. Okay, so that's how you get your importance rating. You pick something which is of high score. Okay, and low scores are something which you may not want to uh, 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 work really, because if you work on, I mean, you might have heard of Pareto, that 20% things account for 80% of the either failure or customer delights, or customer requirements meet, or whatever. So if you take care of top 20% items which are very important, okay, it will cover 80 to 90% of your kind of design requirements or design compliances. Okay, so now once you have that, okay, what you do is now you have concepts, now you have requirements, now your engineers come with lot of concepts that, hey, I have this 10 concepts. Okay, I want it to be this type of bracket, that type of bracket, heavy bracket, light bracket with rips, and so on. Now what you do, you try to take out the concepts out of those 10 available concepts. Okay, so now what you do is, okay, okay, so now you have one concept, concept 2, concept 3, concept 4. Okay, and now you have your requirements here, I mean criteria or requirements here, that okay, for price, this concept is working well, then positive. This concept is not working well, then negative. This is okay, kind of okay, so neutral, and this is positive. Okay, so these scores basically for your different requirement, for price, for quality, for weight, for strength, and so on. So you have all these concepts, so you try to get your total scores here, weighted sums of negative, positive, add that, you do arithmetic calculation, and you get the scores. And that's how you get to know that, okay, this is now here 30 and this is 30, so these two concepts are superior than these two concepts, so I will pick this concept and I pick this concept. Okay, and kind of cancel this concept here and this concept here. Now this way you kind of pick, let's say in this Pew matrix you are picking 2 concepts out of 4. Okay, so that way if you follow this structured approach, you will have documentation, at the same time you have you record, and a confidence in what you are doing, because it is done with some rational. Okay, and there is one more tool, which is FMEA. I'm not sure whether you guys have heard of this. Now there can be design FMEA, design failure mode and effect analysis, or process FMEA. But what you try to do in FMEA is, you have your failure mode listed. Okay, here, then let's say now the failure mode is, for tank, let's say the failure mode is, okay, it bursts. Okay, why it would burst? Okay, so it is for tank here, the fuel tank here. Okay, and here it bursts. Now fuel tank may burst when, let's say now tank has fuel. Okay, in if it is hot season, the fuel also gets vaporized. There are few basically a few components available which are there to absorb that fuel vapor, but let's say there's nothing available, so you have fuel vapor. Now the moment the pressure of vapor starts increasing at certain stage, it will happen that the fuel tank may burst. Okay, I'm just telling you one hypothetical situation. Okay, that doesn't happen because you have something to control those vapors and absorb those vapors also. So here what you have, potential failure mode here is burst. Okay, now how that burst will affect. So burst, what it will do, it will basically, the moment tank burst, your entire fuel will get leaked and will get, the tank will be empty and you will not have anything to run your engine. Okay, so it has, okay, so it has a very strong effect on your vehicle running. Okay, so on that the effects, the severity of effect, you rate it as very high number. Okay, now you say, okay, now what can be the cause of that fuel tank failure? Okay, so here you have the cause listed. So what can be the cause? The cause can be here that, the fuel vapor pressure increased. That's the cause. Okay, and okay, and there's a next column which says that, okay, that cause is there, I agree, but how, I mean, how likely it is there to occur? I mean, will it happen every time, or will it just happen once, or is it consistent? So based on that, if it is consistent, then occurrence is very high number. If it is once in a while, you say that, okay, this may be just once in a while, temperature might have exceeded above this or something. The truck was already in hot environment, and there's something came near truck which was kind of, which had hot water or something like that. So it happened just once, but it will not happen consistently. So in that case, this will have low score, but if it happens consistently, it will have high score. Okay, and then comes your, how can you control it? I mean, basically, you know uh, that, can you really control it, and can you measure it? Okay, so all these, now detectability comes in, control comes in. Okay, so detectability, occurrence, your effects, these three basically will constitute your RPN. Okay, this is RPN. And what you do is, for different failure modes, now let's say here, for tank, one may be burst, second may be fatigue failure. Okay, third may be your, uh, what can tank do? Tank maybe, third is that it is not, the tank's valve is not working well, the fuel is not getting filled properly. So for all these failure modes, for tank itself, you may have some, 5 to 7 failure modes, and for that you have respective RPN based on the effect and the occurrence and the detectability. So what you do is, you pick, typically you pick first high RPN failure modes. Okay, and you try to resolve that, and then you go for lower ones. Typically above 100 are the RPNs. If you have in your chart, they are picked first, and then you work on those RPN and you try to, resolve those issues. And that's how you take care of your failure modes. So it's a live document. I mean, the moment you change your design, your FMEA will get revised, because your RPN number will get revised. Now, it may have, you might have not had earlier, control or detectability, but now you have better control, better detectability, so your score will vary accordingly. Okay, so this FMEA has to be updated after, during your product design. Okay, so this is how you kind of, consolidate your failure modes, and you work on them in a more focused way. Okay, and then comes, okay, one topic which I thought, okay, again, maybe in a deep, which is DOE, design of experiments. Okay, now design of experiments and, optimization using the, uh, your statistical softwares and your statistical methodology, the Gucci's and all those. So okay, so in design of experiments, what you do is, now let's say in your bracket itself you come with, okay, now I go to component level, to make it little more clear. So in component, let's say in particular rib, you have width, you have length, sorry, width, you have thickness, and you have angle. Okay, so you want to see that, okay, in how my design is changing in the some range of width minus W to plus W.